Tremendous honor to speak here, especially since the topic I'm going to talk about has so much to do with many people sitting in this room. So let me start from some motivations. So let's recall the basic definition of the Hasse-Weil zeta function. So if X is a proper smooth variety over a number field, which for simplicity we just say it's Q, and if P is a prime of good reduction, in the sense that X has a good model over ZP, then we can define its zeta factor at P to be the sort of generating series of point counting on the special fiber of X. So it's the exponential of this point counting so script X is a certain good model for X, and you count the number of FPN points on this model, and then you times P to the negative NS over N. Okay, and this guy also has a cohomological interpretation in terms of étale cohomology. So it's product of the so it's the product over the different degrees of the cohomology of the characteristic polynomial of the Frobenius acting on the étale cohomology, and here you set this formal variable t to be p to the negative s. So, in general, we conjecture that this zeta function. So, if you form the product of these local factors, so at least naively, we just take the product over almost all primes P of good reduction, then conjectured, so it is conjectured that this global zeta function should have good analytical properties. Like having meromorphic extension to the whole plane, or functional equations. So the prototypical theorem of my topic today is due to Eichler and Shimura. So it says if you take X to be the modular curve of level gamma naught n, and the compactified version. So it's an algebraic curve over Q. And then you can look at its zeta function, and it will be equal to, so you have two factors of Riemann zeta functions, basically coming from H0 and H2. And the H1 part will be a product of the Mellin transforms of modular forms Fi. So here Fi is a basis of the space of weight to cuspidal modular forms of level gamma naught n. So you take them to be Hacker eigen forms. So this theorem says that if your variety is a modular curve, then we know that its Hasse-Weil zeta function is equal to a product of automorphic L functions. And for automorphic L functions, somehow it is more plausible that you could possibly try to prove good analytic properties of them. So to generalize this, we want to find a relation between Hasse-Weil zeta functions of Shimura varieties and automorphic L functions okay. So I should say that so the original method of Eichler and Shimura to prove such a theorem is through the study of congruence relations between Frobenius and Haeckel operators on the reductions of the modular curves. And it turns out that to generalize to higher dimensions, you need somehow a different strategy. And that strategy, I think, is due to Professor Langland's. So strategy. So basically, you want to study the zeta function of Shimura varieties, and more or less, it is the same to study traces of Haeckel operators and Frobenius on the cohomology of the Shimura varieties. And to prove that the zeta function is equal to a product and quotient of automorphic representations, basically you want to relate these traces on the cohomology with spectral information. So here by spectral information, I mean like parametrizing globally or locally automorphic representations and studying their multiplicities and so on. But we have the trace formula of Arthur and Selberg trace formula, which is a bridge between such spectral information and group theoretical information. So here by group theory information, I mean the geometry of reductive groups. So conjugacy classes inside them and stable conjugacy classes inside them, and integrating test functions on these orbits. And then to establish such an arrow, we try to establish a relation here. So here we can formulate precise conjectures and results, and it will be the topic today. Okay? So we fix a Shimura datum. Gx. So recall that this means G is a reductive group over Q, and X is a certain permission symmetric space of the real points of G. And then such a datum would give you a reflex field, E, which is a number field over Q. And also, for all compact open subgroup of the finite adelic points of G, which we assume are small enough, we would get an algebraic variety she sub k over E, which is quasi-projective and smooth. At least if you assume k is small enough, and such that its C points recovers this familiar double quotient So GQ by X times G of finite dels mod K. Okay? So let me write down two examples. So firstly, if you take G to be GL2, and you take X to be the upper and the lower half plane, then you get the theory of modular curves. Upper and oh, okay, thank you. Yeah, so it's the union of two. Yeah, it's not either upper or lower. It's the union of the two. And the second example is the main topic of my talk. So you take V to be a quadratic space, which just means a vector space with a quadratic form on it over Q of signature and 2, and you take G to be the special orthogonal group of V as an algebraic group over Q, and you take X to be the space of negative definite oriented planes in V tensored with R. Okay, so by plane I mean two-dimensional subspaces, and then you get the theory of orthogonal Shimura varieties. And so here the reflex field is Q, and the dimension of the Shimura variety is equal to n. Okay. So I mean for for small values of n, because of accidental isomorphisms between thinking diagrams, such Shimura varieties will cover some classical examples. But for large n, they're different. Okay, let me erase something. I lost my chalk. Right, so from now on, for simplicity, we just assume that the reflex field is Q. And also, we fix a prime P to be hyperspecial for the level K, in the sense that this K is a product of K upper P and K lower P, with K upper P a compact open subgroup of GAFP, and K lower P a hyperspecial compact of G of QP. Okay. So then, conjecturally, if you have a prime which is hyperspecial in the level, then you expect that your Shimura variety should be of good reduction at P. And this conjecture is also proved for abelian type Shimura varieties by Kissin. So now I can write down the theorem of today. So it says that the following conjecture is true for orthogonal Shimura varieties. Okay, so I need to write down the conjecture. So I think this form of the conjecture is due to Kottwitz around 1990. But I'm sure that such a form should already appear earlier, maybe not in the written down form, but known to people for some time. So it says that the trace of f upper p infinity times phi to the j acting on IH star is equal to sum over h of iota gh and st upper h of f sub h. So let me explain the terms. So this f upper p and infinity is a Hack operator away from p of level k upper p. So I mean, by definition, it's simply a function on this af away from p points of g, which is bi-invariant under k upper p. And this phi is the geometric Frobenius at p, and j is an integer, positive. And this IH star is the intersection cohomology of Xi K bar So where this Xi K bar is the Bailey-Burrell compactification, or sometimes also called minimal compactification, of the Shimura variety at K.
So by intersection cohomology, you mean what?
So by this I mean, so you start with your coefficient system on Xi K, and then you form the intermediate push forward.
It's a middle extension
yes.
to this compactification.
Yes, yeah. And then it's the étale cohomology of this guy with coefficients in that sheaf. Okay? Right, so I should say it's the étale version, so that you can have an action of the Galois group. And also, I mean, implicit in the conjecture is that the Galois action on the intersection cohomology should be unramified at P. Right? So that you have a well-defined action of the Frobenius on this. And Hack operators also act on this, and these two actions commute. So I can write f away from p infinity times phi to the j acting on this. So I can also recall that this Bailey-Burrell compactification, so is a projective and normal algebraic variety also over the reflex field E. But in general, it can be quite singular. So in the one-dimensional example, these are just the x0 ends, and they are smooth. But in higher dimensions, they can be singular. So somehow, for such singular varieties, it's a good idea to take intersection cohomology. And I should say that for the orthogonal Shimura varieties in this talk, they are indeed non-compact. So their Bailey-Burrow compactification is not equal to themselves, and it has so the boundary has a stratification into modular curves endpoints. So the terms on the right-hand side, this H runs through endoscopic data of G. So I mean, naively speaking, there are just a family of quasi-split reductive groups over Q associated to G. And this ST upper H means the stable, the geometric side of the stable trace formula for H. And this F sub H is a prescribed function defined on the adelic points of H. Okay?
What does describe mean?
What does
Just given function?
no?
What do you mean by describe?
Okay, so I can be more precise. So so this function is a product of a contribution from the Archimedean place and at P, and also the contribution away from P and infinity. So away from P and infinity, by definition, it's the Lalands and Shellstedt transfer of the original test function f away from P and infinity. And at P is by definition some twisted transfer of some well-defined special function on the p-adic points of G. And at infinity, it's by definition a prescribed linear combination of pseudo coefficients of discrete series representations of H. Okay. Okay, so I think I have explained all the terms in the conjecture.
Like GH.
Yeah, so this iota GH is a constant that only depends on G and H and does not depend on. So I mean, it can be something like 1 or a half or a quarter. So it does not depend on the Shimura datum, does not depend on J, does not depend on P, does not depend on F away from P and infinity.
Why do only discrete series, I mean, are there no sort of, are you in some dimensions that in the trace formula there may be some representations which might be limits of discrete series?
And I think only
some regularity or something?
not really. I think only discrete series appear. So basically the coefficient system of the cohomology you want to study is some lambda-adic automorphic sheaf on your Shimura variety. So that by definition comes from some algebraic representation of G. And then from this algebraic representation of G, you can so you get a packet of discrete series of G of R. And then this packet also has pre-images in H. So these are basically all the packets of discrete series that you want to consider. Okay. All right. So I think I have explained everything in the conjecture. So now I'd like to make up several remarks. So first remark is that so also have a closely related conjecture. Maybe I call it conjecture 2. Where you simply replace the intersection cohomology by the compact support cohomology of the Shimura variety itself not its Bailey-Burrell compactification, but itself. And on the right-hand side, you replace this full geometric side of the stable trace formula for H by the so-called elliptic part of it. And the test function f sub H is the same. So here, STH sub E is the elliptic part of STH. So conjecture 2 is proved by Kottwitz for PL-type Shimura varieties, or maybe excluding some of them, and also by joint work with Mark Kissin and Su-Woo Shin and myself for Hodge-type Shimura varieties, and some abelian-type Shimura varieties. So we need some restrictive assumptions. Some abelian type. Okay. Are these conjectures inductive?
I mean, if you assume one of them sort of universally, does it imply the other?
Well, that's a question that is very difficult to answer. So I think essentially, yes. So if you assume one, then, well, I mean, so you can view both sides of this conjecture as sort of leading terms of the identity there. So if you already know the equality between the leading terms, then all you have to do is to compute whether the sort of boundary terms are equal. And to prove them, essentially it's the same technique as to prove this. Yeah. So, okay, yeah. So since I have already said this, let me remark that so both sides of this conjecture 2 are in some sense easier to compute than the two sides of conjecture 1. So basically for the left-hand side, it's the trace on the compact support cohomology. So you can directly apply Lefschetz trace formula to compute it as long as you know how to count points on your Shimura variety. So so that means you can compute that the left-hand side is equal to some orbital integrals and some twisted orbital integrals by counting points. And then you have a bunch of these. Then you can apply a procedure called stabilization to get the right-hand side. So that is also because this elliptic part of the stable trace formula is also easy to write down. It's just in terms of stable orbital integrals. So on the left-hand side, you already have orbital integrals and twisted orbital integrals. Then you can just stabilize to get the right-hand side. So basically, that's how this conjecture 2 is proved. But the problem with conjecture 2 is that this elliptic part of the stable trace of the geometric side of the stable trace formula does not reveal spectral information well. So that's why we are not just happy with conjecture 2, but we really want conjecture 1, where you have the whole geometric side of the stable trace formula. Remark 2. So conjecture 1 is also proved for.
Conjecture 1 is conjecture.
Yes. So conjecture is also proved for the Siegel modular varieties associated GSP, and the Shimura variety is associated to GUPQ by Morel around 2010. Sorry. How does it work? Like this?
It's upside down. Thank you so much.
Thanks. Okay. Conjecture, remark 3. So conjecture 1, conjecture together with others conjectures about parameterizing and the multiplicities of automorphic representations implies a full description of the intersection cohomology as a module over the Galois group and the Hacker algebra, and it would also imply automorphy of the Hasse-Weil zeta function of the intersection cohomology. Okay.
Can you break it into different IH of ends?
Different
I mean, no,
IH.
for each, the third intersection cohomology group.
Right.
Using weights you
I mean, you can get this automorphy for that.
can. Yeah.
What does automorphy mean?
Oh, so it means that this zeta function is equal to a product of automorphic a product and quotient of automorphic L functions.
And those, or which ones, ones for which we know meromorphic continuation?
Not necessarily. Yeah.
Almost never.
But for a single intersection cohomology group,
They're like XP of the
it's a product or a reciprocal product. There's no mixing, or there's mixing.
Well, so like just for IH3,
The IH3.
you mean is it equal to a single automorphic L function?
Or is it either a product or 1 over a product, but not something upstairs and something downstairs? That's what I'm asking.
I'm not sure. Yeah. Yeah. Sophie, do you know?
It's nice.
Okay, so the final remark. So the analog of the conjecture, but without Frobenius. So only about the choice of a Hacker operator on the intersection cohomology is due to works by Arthur and Gorski, Kotwitz, and McPherson. And these two works are equivalent by Zucker's conjecture, which is also known, and plus Arthur's stabilization of the invariant choice formula. So basically what Arthur does is he proves that the choice of a Hacker operator on the L2 cohomology of any localist metric space can be expressed in terms of the invariant choice formula. And what GKM does is basically the same, but for the intersection cohomology of the Bailey-Brock compactification instead of L2 cohomology. And Zucker's conjecture states that the intersection cohomology of the Bailey-Borel compactification is the same as the L2 cohomology of the original Shimura variety. So these two are equivalent. And then the trace is already expressed in terms of the invariant trace formula. And then other stabilization in general stabilizes the invariant trace formula to give you some expression like the right-hand side. But these are all without Frobenius.
Zucker's known, right?
It is known around 1990. Yeah. Okay, so now I can talk about the idea of the proof. So the proof is by calculating both sides. So firstly, by the work of Morel, we know how to calculate traces on intersection cohomology in terms of traces on compact support cohomology of the various strata in the Bailey-Borel compactification. So you could express this trace. So this is an abbreviation for the left-hand side. Okay, the trace of the Hacker and Frobenius on the intersection cohomology can be split up into some indexed by Levy subgroups of G up to GQ conjugacy, and they're all defined over Q. I mean, Levy subgroups of G defined over Q up to GQ conjugacy of terms, which I don't specify. So also, for the right-hand side, this stable trace formula of F sub H can also be split into a sum indexed by Q Levy subgroups M prime of H of terms ST HM prime of FH. So here, in this sum, the sort of leading term, trace G, is just equal to the trace on the compact support cohomology of the Shimura variety itself. And here, the leading term here, ST H sub H, is just the elliptic part of the stable trace formula. So by conjecture 2, so for the case proved by Kissin, Shin, and myself, we know that this trace sub G is equal to a sum of iota GH of ST HH of FH. So it's like we already know that the leading terms of both sides agree. Oh, sorry. So by conjecture. So by conjecture 2, in the case proved by okay. So it remains to show that if you sum over the proper Levy subgroups of G, of trace M, should be equal to sum over H of iota GH, and then sum over proper Levy subgroups M prime of H of these stable trace formulas. So these contributions from M prime of the stable trace formula. Okay, so in fact, we can classify some of the pairs H and M prime in terms of Levy subgroups M of G. And we need to show that this contribution of M to the Shimura variety should be equal to the sum of the contributions from pairs H and M prime, which are sort of labeled with M. So I mean, some of the pairs are labeled with M, some of the pairs are labeled with another M, and some of them are labeled with nothing. So if they are labeled with them, then the sum of the contributions of these should be equal to the contribution of M to to the Shimura variety. And also, we need this vanishing result, which says that if you sum over all these pairs that are not labeled to, not classified in terms of any of these, so the rest of them, so the rest of the pairs of the contributions then you should get 0. Okay? So I should remark that this second vanishing result is not automatic from definition, but it also follows from similar calculations in order to prove the first one. Okay. So now let me tell you a bit about what kind of terms show up on both sides of this, for example. So there are contributions from the Archimedean place, and then for them, on the left-hand side, the contributions from the Archimedean place is sort of some kind of truncated group cohomology of the unipotent radicals of parabolic subgroups of G. And for the right, so basically, why do we have such a thing? So this trace M, the contribution of the Levy M to the trace on the intersection cohomology, but basically arises as follows. So by the work of Morel, we know that to compute the intersection cohomology, it suffices to compute compact support cohomology on the various strata in the stratification of the Bailey-Burrell compactification. But here, the compact support cohomology is with coefficients in a very non-trivial local system. Even if you are only interested in the trivial local system on the open part, when you go to the boundary, you get non-trivial coefficient systems. And these non-trivial coefficient systems are basically determined by this truncated group cohomology of unipotent radicals. So terms like these show up on the left-hand side. And for the right-hand side, as I already said before, the Archimedean contribution to this FH is some pseudo-coefficients of some discrete series representations of H of R. So on the right-hand side, we have so basically Harishchandra characters of discrete series representations of H of R, but valued on non-compact maximal tori of H of R. Okay, so basically, if you have a term Hm prime, then you're considering tori which are elliptic inside M prime. So they become non-compact themselves. But I mean, fortunately, there are also formulas for these. I mean, the original so the original character formula of Harishchandra looks simpler when you value them on points in compact tori, but for non-compact tori you also have formulas, and then the goal is to find an identity between linear combinations of them. Right, so I have a bunch of things on the left-hand side and a bunch of things on the right-hand side, and I need to prove that a certain linear combination of the left-hand side and a certain linear combination of these guys are equal. And so the signs of the coefficients in these linear combinations are really important. Okay, so these are the contributions from the infinity. And we also have contributions from from P. So here, for the left-hand side, basically the contribution from P does something like counting points on the boundary strata of the Bailey-Burrell compactification. So in the case of orthogonal Shimura varieties, these are just modular curves and points. And for the right-hand side, so for example, if my M, a Levy of G, looks like something like this, some GL2, so it's R, basis of R looks like GL2 times some SON minus 0 minus to 0. Then there are two kinds of contributions from P. To the right-hand side. So firstly, we have a good kind. So they also behave like counting points on the Shimura variety of GL2, which are just modular curves. So you see, these are good points. These are good terms because on the other side you also find such terms. But you also have bad terms. So bad terms they behave like counting points on the Shimura variety of this other factor, so n minus 2, 0, which do not exist. Do not exist. Basically because this group at infinity has the wrong signature, so there's no Shimura variety associated to it, but yet at p you do find terms that somehow think that they are counting points on such guys. So they are bad terms. So we need to so to show good terms remain. And bad terms cancel after interaction with the signs from the Archimedean calculation. Okay. So that's why I said in the Archimedean calculation, each sign of the terms in the linear combination really matter because you're going to multiply them with the terms from P, and you want anything multiplied with the bad term from P should cancel each other in the end. Okay, so finally, let me just remark that to get signs, so to get correct signs at infinity, so we need to compute the sign between different normalizations of transfer factors for GR and HR in order to get the right signs. Okay, I'll finish here.